They called it the fundamental building block, the smallest piece of reality, the invisible core of all that existence. But they were wrong. Democritus saw it first, an unseen world, a universe made of tiny, invisible pieces, and he called them atoms. But the world wasn't ready. His word faded into dust, lost in time. The universe, it seemed, had no place of such adjustabilities. Hey, buddy, welcome back to the series named In the Search of Schrödinger Cat. In today's topic, we covered how the inside of atom structure changed by the perspective of different peoples like George D.J. Thomson, Bohr, Heisenberg, Einstein, how the research changed the perspective of atom and the quantum mechanics, how their experiments shocked the world, shocked the greatest mind. And I will tell you in a form of a story by which you can easily understand. In the past video, it was only 5 minutes long. I am demonstrating the outer world of that atom. So now we are going deeper into that. So be with me. I hope you will enjoy it. So start with the first man, Dalton. Centuries later, a quiet man named John Dalton breathed life into the forgotten ghost. He saw patterns in elements, rules hidden in their combinations. Atoms, he claimed, were real, solid, invisible. But could something so small truly be unbreakable? The year was 1803. The air in Manchester smelled of coal and damp paper. Inside a dimly into study, John Tuttle sat hunched over his desk, his fingers stained with ink, his eyes fixed on the numbers before him. For years, he had studied gases, searching for the hidden patterns with them. Every experiment whispered the same truth, and the truth is, elements always combined in fixed ratios. It wasn't change, it wasn't chance, it was law, not a chance. Okay? Dalton leaned back. Dalton leaned back, exhaling sharply. But why? He muttered. He's always like confusing. Why this happening continuously? The answer struck him like a thunderbolt. Matter wasn't continuous, it was made of invisible particles named atoms. A knock at the door made him flinched. Thomas Henry entered, his face lean with skepticism. Dalton, you claim matter is made of atoms? Where is your proof? Dalton smiled and gestured towards his notebook. Here's hydrogen, oxygen, nitrogen all exist as tiny, distinct pairs, unchanging and internal. Henry forward, flipping through the pages. This will be impossible to prove, he said. Daniel shook his head. It explained everything, why elements combine as they do, why their weight are consistent. The world must know. A week later, he stood before a royal institution, facing an audience of skepticism scholars. Okay, what is matter? He said. Okay, the room murmured. Said some said fire, some says water, air, and earth, whatever. Others scoffed, believing in invisible force like phlogiston. Dalton lifted a vial of hydrogen. This is not fire, not air. It is an element made of atoms. The room stilled. He described how atoms combine in whole number ratios, forming compounds like bricks from forming house. We don't see this the wind, he argued. Yet it bends trees. Like we can't see air, but it bends the trees. Why do we not see gravity? Why we do not see the gravity? Yet it holds us to the earth. Atoms, through unseen, shape everything. A voice ranged out. Madness. Someone says madness. It's like nothing. Dalton made the man gaze. Truth is often mistaken for madness until it becomes undeniable. Some took furious notes, others scrawled. The old guard of science did not yield easily, but Dalton had planted the seed. The atomic age had begun. Now here comes another man, J.J. Thomson. You all know for math, okay? So, what he said. Science has a cruel sense of irony. The moment Dalton's atom was expected, he shattered. J.J. Thomson saw something unexpected. What he said, now just focus on it. The year was 1897, like a century passed, okay? The world still believed in Dalton's unbreakable atom. Scientists had spent nearly a century convinced that atoms were the smallest invisible building blocks of nature. But inside the dark corridors of the Cavendish laboratory, J.J. Thomson was about to tear that belief apart. For months, he had worked tirelessly sending electric currents to a vacuum tube. Okay? What? Like, listen to me. Watching strange greenish rays emerge from the cathode. These rays, mysterious, weightless, defined explanations. Where the light? Where the particles? The scientist world scroffed. But Thomson saw something no one else did. One night, alone in his lab, he placed metal on either side of the ray and switched on an electric field. His breath caught. A ray bent, not towards the positive plate, but towards the negative plate. This meant only one thing. They were tiny, negatively charged particles. But how? Dalton's atom were supposed to be invisible. Hertz pouring. He repeated the experiment, refining his measurements. The particles were thousands of times smaller than a hydrogen atom. They were not just inside the atom, they were part of it. He had found something no one had dared imagine. The atom was not solid, it could be broken. When Thomas presented his discovery, the room fell silent. Gentlemen, he announced, atom contain smaller negatively charged particles. It called them corpuscles. Here's the corpuscle perspective starts. And it's only the starting, the building blocks of electricity. The audience erupted. Some dismissed it as nonsense. So when you firstly demonstrate something to the world, that is, if it's new, the world decline. Say nonsense. Rubbish. Okay. Other whispered in alarm. If the atom wasn't invisible, what else had scientists misunderstood? Okay. Soon the world changed. Electricity was no longer a mystery. It followed from the very structure of matter itself. Engineering used its knowledge to refine electronics, leading to the birth of radios, telephones, and even the first step towards modern computers. Dental's indestructible atom had shattered, and science would never be the same again. And here's the golden revolution comes. Something refused to fit the puzzle. Rutherford's experiment should have been predictable, but it wasn't. Some particles passed through the gold foil like ghosts, but others bounced back, as if they had hit something dense, something unimaginable. The atom had a heart, a nucleus, and it was far more smaller and powerful than anyone had dared to dream. Here's another man come, Bohr. You all know Bohr's atom perspective, the orbital perspective, okay? And how it changed the world, we see now. Electrons were unpredictable, chaotic, but Bohr had an idea. What if they were just moving randomly? What if they followed rules? Like, listen to me carefully. Orbit like planets around the sun, like that. But in the new universe, electrons didn't glide, they jumped, disappear from one place and reappear in the another. Never seem in between. The year was 1913 when this was all happening, and the atom was battlefield. Okay, Dalton had declared it invisible. Thomson had shattered it, revealing electrons. Then come Rutherford, who fired particles in a golden foil and found that atom had dense charged nuclei. But something was wrong. Rutherford model could not explain why electrons didn't spiral into the nucleus and destroy the atom. Okay, if it's spiraling around that in a random way, why it's not like compress in a nucleus and then explode? Okay, why they are stable? That's the question. It was the shadow of Copenhagen. A young Danish physicist named Niels Bohr studied these considerations. Okay, his mind racing. The atom was a puzzle, and he was determined to solve it. Late into the night, he scribbled equation, staring at spectral lines, light emitted by atom in distinct colors, like spectral lines, the black lines in the light spectrum. Okay, why this happening? The answer was hiding in light itself. Bohr realized that electrons couldn't move freely around the nuclei. They had to stay in fixed orbit, like planets circling around the star. And when they jumped between these orbits, they absorbed or emitted energy in precise amount named quanta. It was radical. It was unthinkable, but it worked. As soon as with tremble hands, he published his theory. Electron did not spiral inwards. He wrote, they moved in a quantized orbit. The atom is stable because nature obeys strict energy rules. The scientific world revealed some called it genius, other madness, same as the J.J. Thomson, okay? Bohr's model explained the mystery of atomic spectra, providing that atoms weren't just a tiny solar system. They followed the strange laws of quantum mechanics. His theory changed chemistry, physics, and the future itself. When Bohr atom, when Bohr's atom, scientists could not predict how elements now, could not could now predict how elements behave, unlocking the secret of periodic table. It leads to laser, transistor, nuclear energy, and the quantum world beyond imaginations. The atom war had regret for a century, but with Bohr, the rules were realistic and reality itself had changed. And here's comes in another man with their cat. Now you know what the name of the man is, named Schrödinger. We all know Schrödinger's cat experiment. So the year was 1935 and the world of physics was in chaos. Bohr had given the atom in orbits, but then came Heisenberg, whispering a terrifying truth. Electrons weren't even real objects, they were probabilities, mere ghost of existence. The certainty of science was unrevealing. In a dimly lit study of Vania, Erwin Schrödinger sat at his desk, his fingers grabbing a pen. I had spent years whistling with quantum mechanics, and what he found disturbs him. If Heisenberg was right, reality itself was uncertain. But how could that be? He closed his eyes, then smiled darkly. If quantum mechanics were true, then he could create an impossible paradox, an experiment so absurd it would expose the madness. He imagined a cat locked inside a box alongside a vial of poison triggered by the decay of an atom. Quantum mechanics said the atom exists in both decay and undecay states until it observed. But what of the cat? Was it alive or dead at the same time? About the perspectives, okay? Schrodinger's cat became a nightmare of physics. It forced scientists to confront of horrifying possibilities that reality wasn't fixed until someone looked at it. The atom was no longer just a particle or a wave. It was a question mark, waiting for an answer. His thought experiment changed everything. It led to quantum superpositions, the multiverse theory, and the birth of quantum computing. Science had chased the atom for centuries, but now the atom laughed back. The deeper they look, the stranger reality becomes. And here's the Heisenberg comes. Okay, the atom had been cracked open, but instead of answer, it breathed a nightmare. In 1927, Werner Heisenberg stood before a blackboard filled with equations. A blackboard, okay? His hands troubling his discoveries was terrifying. Electrons were just unpredictable. They were unknowable. No one could measure both their position and momentum at the same time because they are continuously moving. If you Check, if you measure their speed, they are now changing their position. They are not they at their position when you are measuring the speed. And when you measure their speed or like position, they change their momentum. Okay, so the universe had limits. Reality was uncertain.